Transportation network features provide the planner with locations, routes, and attributes associated with roads, railroads, and transit services. The transportation network includes characteristics of intersections and turn locations. Network links contain attributes that define speed limits, capacity, and functional classification. Traffic analysis zones represent geographical units with homogeneous and/or similar land use characteristics. TAZs, as they are known, are traditionally based on census and political boundaries or some other identifiable ground feature. Imagery may represent a cost-effective and efficient data source to create, update, and maintain transportation networks and traffic analysis zones. This video provides an overview of transportation network and traffic analysis zone creation, update, and maintenance using imagery sources. For road networks, we will discuss sources of data, research on automated extraction, and methods of manual digitizing using aerial and space imagery sources. For traffic analysis zones, we will discuss use of imagery to support boundary delineation, centroid creation, and linking zones to the network. There are many sources of road network data, both public and commercial. These data may require additional attribution to support travel demand modeling. Commercial vendors are beginning to enhance their existing street network data with specific transportation-related fields, such as turning restrictions, and it is likely that the spatial and thematic accuracy and quality of these data will continue to improve over time. During recent data development to support the TransSIM's implementation, Metro, the Portland Metropolitan Planning Organization, used Tiger Line data to create its all-road network file. Metro had an existing stick figure network file in ME2 format. Metro used custom ArcView scripts to transfer attributes from its ME2 network to the corresponding line segments in the Tiger Line data. In personal correspondence, Metro staff concluded that the effort required in this attribute transfer exercise may have been better spent by creating the network file from scratch through manual digitization of the road network from aerial or space image sources. The Federal Highway Administration is in the process of building, with great assistance from the states, the National Highway Planning Network. NHPN is a 400,000-mile network consisting of the national highway systems and remaining principal arterials and rural minor arterials. FHWA views the FHWA GIS as a tremendous analytical tool to support both national and statewide planning efforts. Large-scale digital line graph data from the U.S. Geological Survey are digitized primarily from 1 to 24,000 scale USGS topographic quadrangles. The basic applications of DLG data are to support automation of cartographic processes and automated spatial data analysis. DLG represents all categories of spatial data represented on a conventional line map, as well as several thematic categories, including hydrography, political, culture, and transportation features. There are several sources of transportation network data available in the commercial marketplace. These commercial products range from map-based products to ones that support navigation mapping in automobiles. TransMap came out of research initiatives undertaken at Ohio State University. It now represents one of several van mapping alternatives available in the U.S. The TransMap van is mounted with several cameras and with GPS to provide near-continuous photo coverage of transportation infrastructure, including roads and highway infrastructure and assets. The resulting photo coverage could be the basis of road networks for use in travel demand models. It is unlikely that road feature extraction will be necessary for most metropolitan areas, since there are numerous existing digital map networks that can be used as a base. For the purposes of this video, however, we thought it would be useful to discuss automated road network extraction, since there is and has been a great deal of research focused on automated network extraction. Such efforts could prove useful in newly developed regions. Automated procedures can be used to support extraction of linear networks from imagery. Once linear features have been identified in imagery, an analyst can use manual tools to create, maintain, and update road networks using image display, vector editing, and attribute tagging. Manual digitizing of road networks is still the most accurate technique available to create, maintain, and update road network data. The San Diego Association of Governments has used high-resolution imagery to assist in accurate model coding of mid-block and intersection lane configurations. Signal-controlled intersections can be distinguished from two-way stop, always stop, rail crossings, and uncontrolled intersections. One-way roads are distinguishable from two-way facilities, and direction coding can be verified. Certain intersection turn moves that are not allowed on the road can be identified and prevented in model networks by coding turn prohibitors. Imagery may need to be reprojected to match data within your existing GIS as a first step in integrating imagery. Imagery will likely need to be processed to account for distortion effects due to camera orientation and terrain in a process known as orthorectification. The resulting orthophotography is high accurate imagery data that can be integrated into an existing GIS. In a 1981 article published in volume 807 of the Transportation Research Record, Karsten Bass provides 10 guidelines to support the delineation of TAZs. These are: achieve maximum homogeneity within the zone, return a maximum of interaction between newly established zones or a minimum of intrazonal trips, limit the number of trip-ins for the newly created spatial entity in order to avoid overloading the adjacent street network in the assignment phase, respect physical, political, and historical boundaries, avoid undesirable shapes of newly created zones, group only adjacent spatial units, generate only connected zones, avoid the formation of islands, obtain a zonal system in which the number of households, population, area, or trips generated and attracted are nearly equal. Base the delineation of the zonal boundaries on census boundaries. In a 1991 article published in volume 1305 of the Transportation Research Record, Anderson discusses the use of GIS to disaggregate Montgomery County, Maryland's 246 traffic analysis zones into 945 smaller subzone components to support finer-grained modeling results. Anderson used several data sets to support the analysis, including tax assessor parcel data, vector data, metro rail and commuter rail stations point data, and sidewalk and street mileage files. In a 1994 Transportation Research Record article, Binion and O'Neill discuss further issues associated with the use of GIS modeling techniques to aggregate GIS data into TAZs. The Baltimore Metropolitan Council, also known as BMC, used imagery to create a new 2000 TAZ for the Baltimore region within a 1-month time period. BMC used 2,000 census block groups in a project sponsored by the Federal Highway Administration and the U.S. Census Bureau known as TAZ Up, or TAZ Update. The results of the effort were used to support the development of the 2000 Census Transportation Planning Package. BMC evaluated the TAZ boundaries based on population and employment forecasts for the year 2020. This graphic illustrates TAZs in red that are projected as having a larger population figure than that provided in the TAZ boundary creation guidelines referenced earlier. This graphic illustrates TAZs in red that have higher employment forecasts than that prescribed in the guidelines. BMC staff implemented the TAZ update to create new TAZs that conform to transportation planning engineering guidelines. During their verification of TAZ boundaries, BMC staff noted that some features were not contained in the Tiger Line files. BMC staff used 10-meter spot imagery that was distributed in the Maryland Department of Planning Maryland Property View data. Imagery data was used to verify that features that BMC staff had selected for TAZ boundaries did, in fact, have corresponding observable features on the ground. This example shows a power line that was used as a TAZ boundary. The San Diego Association of Governments, also known as SANDAG, uses imagery to support TAZ analysis. Imagery is used to identify and update access links to the transportation network from the centroids of TAZs. SANDAG generally uses 1 to 4 access links per zone. Once centroids are identified, the volume of traffic for the zone is loaded at that network access point. As we have stated earlier in this video, imagery provides a useful backdrop for display, analysis, and update of TAZs. Commercial GIS software can be used to modify TAZ boundaries based on new information, including that from imagery. The GIS vector editing software provides the capability to split boundaries, add new boundaries, and shift existing boundaries. In this example, we illustrate the use of vector edit tools to create general feature data. Imagery provides the backdrop from which points can be selected and linear network features created. This video has provided information on ways that imagery can support road network and traffic analysis zone creation, update, and maintenance. We have provided several visual examples showing how imagery can support this important transportation planning task. This video has just touched the surface, however, on ways that imagery software, and GIS software can support network maintenance and update. Further information is contained in the use of imagery in transportation planning, a guidebook that was developed and which is being distributed by the Federal Highway Administration.